Tonight we dive into one of the most mind-bending mysteries in all of physics. Imagine two particles, separated by entire galaxies, yet somehow instantly aware of each other's actions. Einstein once mocked it as spooky action at a distance. But this isn't science fiction, it's a proven phenomenon. From powering quantum computers to enabling teleportation, from creating unbreakable encryption to challenging our understanding of space and time itself, this mysterious phenomenon known as quantum entanglement may hold the key to the true nature of reality. In this documentary, we'll trace the story from Einstein's skepticism to cutting-edge experiments spanning continents and even reaching into orbit. We'll uncover how something so invisible, so seemingly impossible, is now reshaping the future of science and technology. But the deeper we go, the stranger the picture becomes. What if quantum entanglement isn't just a rare curiosity, but the very foundation of existence itself? Stay with me, because what you're about to discover could completely transform the way you see the universe. So, how do we even begin to understand this mysterious phenomenon known as quantum entanglement? It sounds like something straight out of science fiction. It behaves almost like magic, and yet it stands as one of the most thoroughly tested and mathematically verified aspects of quantum physics. But to truly grasp what it means, and why it could be the most profound clue to understanding the true nature of reality, we first need to clear away a few misconceptions. Imagine two particles born from the same parent particle in a powerful high-energy event, perhaps deep within the confines of a particle accelerator, or even during the chaotic first seconds after the Big Bang. These two particles separate and drift apart, possibly across vast cosmic distances, millions of kilometers, maybe even light years. Yet something extraordinary occurs. The moment you measure one particle, its spin, its polarization, or its energy, the other reacts instantly as though the two are still connected by an invisible thread. No signals are exchanged, no messages transmitted, and no time delay occurs. It's as if the particles know what the other is doing, defying every conventional rule of space and time. This bizarre phenomenon is what physicists call quantum entanglement. But it's not some error in measurement or a strange loophole in physics. It's a fundamental feature of how nature truly works. It's one of the strangest and most debated ideas in science, a concept that Albert Einstein famously rejected, labeling it spooky action at a distance, while Niels Bohr passionately defended it as a core principle of quantum theory. Decades later, experiments have confirmed what once seemed unthinkable. Scientists have entangled photons, atoms, and even complex molecules, and each time the eerie connection remains. Entanglement shakes the very foundations of what we believe about reality. It challenges the idea that space separates objects, that every effect must have a cause within time, and that information cannot move faster than light. These principles form the backbone of classical physics, yet entanglement seems to bypass them effortlessly. To understand just how revolutionary this is, we need to revisit what quantum mechanics actually tells us about the world. In our familiar classical reality, a particle is just a small, solid thing, a definite object with measurable properties. It exists in a specific position, moves with a precise velocity, and carries a well-defined amount of energy. You can observe it, track it, and predict where it will go next. But in the quantum world, that certainty collapses. Before you observe it, a particle doesn't have a fixed position or energy. It exists as a cloud of probabilities, a wave function, representing all the possible states it could occupy. In this strange framework, observation itself changes everything. The act of measurement forces the wave of possibilities to collapse into a single outcome. Until that moment, the particle isn't here or there. It's both, everywhere and nowhere, all at once. This isn't speculation, it's the heart of quantum theory, verified countless times through experiment. Now, when two particles become entangled, their wave functions merge into a single shared quantum state. This means that the properties of one particle are inextricably linked to the other, even if they're separated by light years. When you measure one particle's state, you instantly define the others, no matter how far apart they are. The universe doesn't seem to treat them as two separate entities, but rather as two parts of one unified system. This is where things become truly strange. If information can't travel faster than light, as Einstein's theory of relativity insists, then how do entangled particles remain perfectly coordinated across impossible distances? It seems as though quantum reality ignores the cosmic speed limit altogether. For Einstein, this was unacceptable. It violated the very notion of locality, the principle that objects can only influence each other through direct interaction. But for Bohr and the pioneers of quantum mechanics, entanglement wasn't a bug. It was the clearest sign that our understanding of reality needed to evolve. Today, modern experiments have left little doubt. Quantum entanglement is real. We've seen it happen not just in small lab setups, but in large-scale demonstrations. Entangled photons have been transmitted through fiber optic cables across cities, and even between satellites and ground stations separated by hundreds of kilometers. The European Space Agency, China's Messius quantum satellite, and NASA have all performed successful entanglement-based communication tests, pushing the boundaries of what's possible. Still, the implications are staggering. Entanglement doesn't just question how information moves. It challenges the very meaning of separateness. It implies that, on a fundamental level, the universe is not a collection of isolated parts, but a deeply interconnected whole. Space and distance may not be barriers at all, but illusions born from a deeper, unified quantum field. So when we talk about two particles knowing each other's states, we're really confronting a reality where the distinction between one object and another begins to blur. They're not exchanging information faster than light. They're simply reflecting the same shared quantum existence. And perhaps that's the deeper message hidden within entanglement, that everything in the universe, from the smallest particle to the largest galaxy, may be bound together in ways our minds can barely comprehend. When we make a measurement in the quantum world, we collapse a cloud of possibilities into one specific reality. Think of it like a coin suspended in a blur of heads and tails, existing as both until you actually look at it. The moment you observe it, that blur disappears, and it becomes one definite outcome. This is the strange dance of the quantum world, and it becomes even more puzzling when entanglement enters the picture. In the case of entangled particles, their wave functions aren't separate anymore. Instead, they merge into a single shared wave function that describes them as one inseparable system. That means you can't talk about one particle without referencing the other, no matter how far apart they drift. In a sense, they stop being individual objects and start behaving as one unified entity stretched across space. For instance, if you measure one electron's spin and find it pointing up, the spin of its entangled partner will always point down. This isn't because one particle sends a signal to the other or influences it in real time. Rather, both results were part of a shared quantum state from the very beginning. The universe doesn't decide which spin is up or down until a measurement is made. But once that decision happens, the other particle's state instantly becomes fixed, as if reality itself updated in a single stroke across space. This concept deeply unsettled Albert Einstein. He refused to accept that the universe could behave this way. To him, it implied either faster-than-light communication or, even worse, that particles didn't have definite properties until someone looked at them, a notion he found unacceptable. He famously mocked this phenomenon as spooky action at a distance. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, formalized his objection in what became known as the EPR paradox. They argued that quantum mechanics, while successful, must be incomplete. There had to be hidden variables, unseen factors determining outcomes behind the scenes, that quantum theory simply failed to account for. If those hidden variables existed, then reality would still be local and deterministic, and there'd be no need for spooky correlations that violated common sense. But not everyone agreed. Niels Bohr, Einstein's longtime philosophical rival, countered with a very different view. Bohr insisted that Einstein's assumptions about reality were outdated. The problem wasn't with quantum mechanics, it was with our classical intuition. According to Bohr, the properties of a quantum particle don't exist in any definite way until they are observed. Asking what spin or position a particle really has before measurement, he argued, is meaningless, like asking what color a sound is. In Bohr's interpretation, reality itself is participatory. The act of measurement doesn't just reveal information, it defines it. Observation shapes existence, collapsing the fuzzy landscape of probabilities into the solid outcomes we experience. This idea shattered centuries of scientific thinking, suggesting that the observer and the observed are fundamentally connected in ways the classical world never imagined. Einstein found this deeply troubling. He believed the universe should be objective and independent, that things must exist whether or not we're looking. But as experiments grew more advanced over the decades, evidence began piling up against him. Quantum entanglement wasn't just a mathematical trick or a philosophical debate anymore. It was a measurable, observable phenomenon. In the 1960s, physicist John Bell developed a way to test the idea of hidden variables through what became known as Bell's theorem. If Einstein's local realism were true, then measurements of entangled particles would follow certain statistical limits. But if quantum mechanics were correct, those limits would be violated. In the 1980s, physicist Alain Aspect performed a series of experiments that confirmed the predictions of quantum mechanics beyond doubt. The results showed that no hidden local variables could explain the correlations. Entanglement was real, non-local, and undeniably strange. Over the years, the tests became even more precise. Scientists used entangled photons shot across kilometers, then across cities, and eventually between satellites and ground stations in orbit. Every time, the results pointed to the same unsettling truth. Quantum entanglement defies the limits of space and time as we understand them. What started as Einstein's philosophical objection evolved into one of the most revolutionary discoveries in modern science. Quantum entanglement isn't just a theoretical curiosity anymore. It's the foundation for emerging technologies. Quantum computers rely on entangled qubits to process information in parallel. Quantum cryptography uses entanglement to create unbreakable communication links. And quantum teleportation, the instant transfer of information between particles, has already been demonstrated experimentally. But beneath all these practical breakthroughs lies something even more profound. Entanglement challenges the very structure of reality. It suggests that the universe might not be a collection of independent parts, but rather a deeply interconnected web, a single quantum whole in which distance, time, and separation are illusions born from our limited perception. For Einstein, that conclusion was unacceptable. For modern physicists, it may be the key to unifying quantum mechanics with the fabric of space-time itself. And as our understanding deepens, one thing becomes increasingly clear. The spooky action that once haunted Einstein may in fact be the universe's most fundamental truth. For decades, the argument over the true nature of quantum mechanics lingered unresolved. The equations worked flawlessly, predicting experimental results with astonishing accuracy. Yet the philosophical meaning behind those equations remained deeply unsettling. Was quantum entanglement merely an illusion, a mathematical trick masking our incomplete understanding of reality? Or was it a genuine physical phenomenon that forced us to rethink the very foundations of space, time, and causality itself? Everything changed in 1964. That year, Irish physicist John Bell published what became one of the most important theorems in modern science, Bell's theorem. He proposed a precise mathematical inequality that could finally distinguish between Einstein's vision of a hidden variable universe and the inherently probabilistic world of quantum mechanics. According to Einstein's view, if hidden variables truly governed the outcomes of quantum measurements, then experiments involving entangled particles would always satisfy Bell's inequality. But if the predictions of quantum mechanics were correct, if entanglement was genuinely non-local, then the inequality would be violated. For the first time in history, there was a way to test the spooky action at a distance that Einstein had so strongly rejected. This wasn't just a technical step forward, it was a turning point in our understanding of reality itself. The question at hand wasn't simply whether particles could influence each other across space. It was whether the universe itself was built on separable parts obeying classical causality, or whether everything was fundamentally connected beyond the limits of space and time. And when those experiments were finally performed, the results were stunning. Again and again, nature sided with quantum mechanics. Bell's inequality was violated, leaving no room for hidden variables that could preserve Einstein's sense of locality and realism. The spooky correlations weren't a trick of incomplete knowledge. They were real, physical, and woven into the fabric of the cosmos. Before we dive into those groundbreaking experiments, though, it's important to step back and realize what's truly at stake here. This debate isn't only about particles or mathematical equations. It's about the fundamental structure of reality. If quantum entanglement is real, and all evidence indicates that it is, then the universe is far more connected and unified than we ever imagined. We're not built from isolated classical particles bouncing around in empty space. Every atom, every molecule, every cell in our body is part of a vast network of quantum systems intertwined with one another. And if entanglement can persist across immense distances and even across time, then perhaps nothing in existence is ever truly separate. Maybe every object, every being, every phenomenon is linked by invisible quantum threads, connections that quietly stretch through the cosmos, binding cause and effect in ways that challenge everything we thought we knew. This realization has profound implications. It reshapes not only how we understand physics, but also how we think about the universe and our place within it. It suggests that separation might be an illusion, that beneath the surface of reality there is only unity. But such a radical idea didn't appear out of nowhere. To understand how we reached this point, we need to return to the early days of modern physics, a time when the very definition of reality was being rewritten. Nearly a century ago, science experienced a revolution that forever changed our view of the universe. For centuries, classical physics established by Isaac Newton reigned supreme. It painted a world that was orderly, predictable, and deterministic. In Newton's universe, every event had a clear cause, and with enough knowledge, if you could know the exact position and momentum of every particle, you could, in theory, predict the entire future of the cosmos. It was a mechanical clockwork reality governed by certainty and logic. Then, in the early 20th century, that certainty began to crumble. A series of strange discoveries at the atomic level revealed behaviors that defied classical explanation. Electrons behaved like both particles and waves. Energy was exchanged in discrete packets called quanta. Light could act as a particle in one experiment and a wave in another. These puzzling results led to the birth of quantum mechanics, a new framework built not on determinism, but on probabilities. In this new world, particles weren't tiny billiard balls with fixed properties. They were described by wave functions, mathematical expressions representing all possible outcomes that a measurement could reveal. Reality, it turned out, wasn't fixed until someone observed it. In this view, measurement didn't merely uncover what was already there, it created the outcome. The act of observing forced the quantum system to choose a specific state, collapsing the wave function into a definite result. This idea disturbed many great minds, none more so than Albert Einstein. Ironically, Einstein himself had helped lay the groundwork for quantum theory, explaining the photoelectric effect and introducing the concept of light quanta, or photons. but he couldn't accept the philosophical consequences of the theory he helped create. Einstein had spent his career revealing the deep order underlying nature, from the constancy of the speed of light to the curvature of space-time itself. The probabilistic, indeterminate world of quantum mechanics ran counter to everything he believed about reality. He famously remarked, "God does not play dice with the universe." To Einstein, the idea that the universe was fundamentally random, that reality didn't exist until it was measured, was unthinkable. He insisted that there must be deeper laws, hidden variables, operating beneath the apparent chaos of quantum mechanics. But the more physicists tested the predictions of quantum theory, the more they found themselves confronted by results that defied Einstein's expectations. The mathematical beauty of the theory couldn't be denied, and its experimental success was unmatched. Yet, its implications, that the universe might be non-local, interconnected, and shaped by observation, remained as unsettling as ever. This is the tension that defined 20th century physics, the clash between Einstein's classical realism and the bizarre probabilistic vision of the quantum world. And as the decades unfolded, experiment after experiment would push us closer to an astonishing conclusion, that reality itself is quantum at its core. What began as a philosophical dispute between two of the greatest scientific minds became the foundation of modern physics. And the strange truth of quantum entanglement would go on to influence everything from computing and communication to our understanding of the universe's deepest structure. The dice that Einstein refused to believe in, it turns out, may not only be rolling, they might be rolling everywhere, connecting everything all at once. In 1931, Albert Einstein began to push back harder against the strange and counterintuitive implications of quantum mechanics. The theory, which had already revolutionized physics, seemed to him incomplete, a statistical tool that described probabilities rather than certainties. To Einstein, this was unacceptable. He believed that beneath the randomness of quantum behavior, there must exist a deeper, hidden reality governed by precise, deterministic laws. Over the next few years, he devised a series of thought experiments to expose what he saw as flaws in the quantum worldview. These explorations culminated in a groundbreaking collaboration with two younger physicists, Boris Podolsky and Nathan Rosen. Together in 1935, they published a paper that would become one of the most famous and controversial in the history of science. Can quantum mechanical description of physical reality be considered complete? This paper introduced what is now known as the EPR paradox, a thought experiment that questioned whether quantum mechanics could truly describe reality as it is. The EPR argument was deceptively simple but conceptually explosive. Imagine two particles that interact briefly, for instance during a decay event, and then move far apart. According to quantum mechanics, their states become entangled, meaning their properties are correlated no matter how far they travel from one another. If an observer measures one particle's position, they instantly know the position of the other. Likewise, if they measure one particle's momentum, the other's momentum is immediately determined. But this creates a dilemma. According to Heisenberg's uncertainty principle, you cannot simultaneously know both the position and momentum of a single particle with perfect accuracy. Yet, in the EPR setup, by measuring one property of the first particle and another property of the second, you seem to know both, indirectly but completely. To Einstein, this implied that the second particle's properties must have existed prior to measurement. The universe could not simply decide what values to produce at the moment of observation. This reasoning led Einstein to a bold conclusion. Quantum mechanics, while powerful, was incomplete. It was missing hidden variables, underlying parameters that predetermined the results of quantum measurements, but which remained hidden from our instruments. In Einstein's view, the wave function, the mathematical heart of quantum theory, was not a complete description of reality. It merely expressed our ignorance of those deeper variables. Niels Bohr, Einstein's philosophical rival and one of the founders of quantum theory, strongly disagreed. His rebuttal to the EPR paper, published shortly afterward, was as enigmatic as the theory itself. Bohr argued that Einstein's entire line of reasoning missed the essence of quantum physics. To Bohr, the EPR team's assumption that particles possessed definite properties prior to measurement was misguided. Measurement, he argued, wasn't just a passive act of discovery. It was an active part of the physical process. According to Bohr's Copenhagen interpretation, asking about the independent properties of a particle before measurement was meaningless. The act of observation and the context of the experiment defined the outcome. In other words, reality was not independent of observation, it was shaped by it. To Bohr, quantum mechanics wasn't incomplete. It was simply describing a world that operated on principles far beyond classical intuition. That same year, another great physicist, Erwin Schrödinger, weighed in. In a letter written shortly after the EPR paper, he coined the term Verschränkung, or entanglement, to describe the phenomenon Einstein found so troubling. Schrödinger recognized that this strange interconnectedness between particles was not an odd side effect of quantum theory, it was the central feature that defined it. "I would not call entanglement one," he wrote, "but rather the characteristic trait of quantum mechanics." Schrödinger went even further than Bohr and Einstein. He realized that entanglement could extend beyond simple systems of paired particles. It could involve atoms, molecules, and potentially even macroscopic systems. This insight led him to formulate one of the most famous thought experiments in science, Schrödinger's cat. In his hypothetical scenario, a cat is placed in a sealed box containing a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers the release of the poison, killing the cat. Quantum mechanics dictates that until the box is opened and observed, the atom exists in a superposition of decayed and undecayed states, and therefore the cat is both alive and dead at the same time. Schrödinger intended this thought experiment as a critique, a way to show how absurd it seemed to apply quantum rules to everyday life. But ironically, his cat became the ultimate symbol of quantum weirdness. It illustrated the unnerving idea that reality doesn't settle into a definite state until observation collapses the wave function. The boundary between the quantum and classical worlds was not as clear as scientists once thought. By the mid-1930s, the scientific community was deeply divided. On one side stood Einstein, seeking a deterministic universe, local, objective, and complete. On the other side were Bohr and Schrödinger, embracing a reality that was probabilistic, uncertain, and fundamentally non-local. The debate raged on, not through experiments but through philosophy and thought. For decades, it seemed unsolvable. Then, in 1964, a quiet physicist named John Bell, working at CERN, changed everything. Dissatisfied with the purely philosophical arguments, Bell derived a mathematical inequality that provided a way to test whether Einstein's hidden variables could exist. His theorem demonstrated that if the world were governed by local hidden variables, then certain correlations observed between entangled particles would always stay within specific statistical limits that came to be known as Bell's inequalities. However, if quantum mechanics were correct, if entanglement were truly non-local, then experiments should violate those limits. Bell had done something extraordinary. He had turned a philosophical argument into a testable experiment. Suddenly, the question of whether entanglement was real could be settled empirically. Nearly 3 decades after the EPR paradox was proposed, the first experimental tests began. In 1949, long before Bell's theorem was formally developed, Chinese-American physicist Chen-Xiong Wu and her collaborator Irving Shaknoff conducted early studies on photon correlations. They weren't testing Bell's inequalities, those hadn't been formulated yet, but their results hinted at the strange statistical fingerprints of entanglement. Their pioneering work quietly laid the groundwork for future investigations. Fast forward to 1972, when physicists John Clauser and Stuart Friedman conducted the first experiment explicitly designed to test Bell's theorem. They used calcium atoms to emit pairs of entangled photons and then measured their polarizations at different angles. If Einstein's view was correct, the measured correlations would remain within the classical bounds defined by Bell's inequality. But when the data came in, the inequality was violated. Quantum mechanics had triumphed. Still, questions remained. The early experiments were groundbreaking but imperfect. They suffered from potential loopholes, experimental weaknesses that skeptics could point to. One was the detection loophole, which suggested that not all photons were being measured and that the subset detected might bias the results. Another was the locality loophole, which meant that the detectors might somehow influence each other, possibly through unknown signals traveling between them. Then, in the early 1980s, a French physicist named Alain Aspect stepped into the picture. Working at the Institut d'Optique in France, Aspect and his team designed a series of increasingly refined experiments to close those loopholes. They improved detector efficiency, randomized detector settings in real time, and ensured that the two measurement events were truly independent. The results were unambiguous. Bell's inequalities were violated again. Entanglement was not only real, it was unavoidable. Nature itself operated according to quantum rules that defied classical notions of separability and locality. But physicists are meticulous by nature. The extraordinary implications of entanglement demanded equally extraordinary evidence. Over the next few decades, experimental techniques continued to evolve. Finally, in 2015, the definitive loophole-free Bell tests were achieved. 3 independent teams in the Netherlands, Austria, and the United States performed experiments that simultaneously closed all major loopholes. At Delft University of Technology, researchers used entangled electrons trapped in diamonds with measurement settings determined by random number generators operating faster than any possible signal could travel between detectors. Once again, quantum mechanics won decisively. The results were clear. The universe does not obey classical locality. There are no hidden variables restoring the comforting determinism Einstein longed for. Quantum entanglement is real, measurable, and deeply woven into the structure of reality. What began as a philosophical dispute between two giants of physics became one of the most profound revelations in science. Entanglement wasn't a glitch in the theory. It was a window into the true, interconnected nature of the universe. Reality, as it turns out, is far stranger than even Einstein could have imagined. The measurement stations were placed far enough apart that even light couldn't have traveled between them fast enough to coordinate a response. The outcome was astonishing. Quantum mechanics had once again triumphed. Bell's inequalities were decisively broken, and the idea of local hidden variables, the cornerstone of Einstein's argument, was finally laid to rest. The results made it clear. The universe genuinely allows for non-local connections. The measurement outcome on one side of an experiment could not be explained by any signal traveling through space at or below the speed of light. Entanglement was no longer just a mathematical abstraction or a peculiar theoretical prediction. It was now a proven and reproducible phenomenon of the natural world. What made this even more remarkable was its consistency. Entanglement wasn't limited to rare, unstable conditions. It was universal, something that could occur anywhere under the right conditions. But nature, it turned out, still had far more surprises to offer. In 2017, scientists at the Chinese Academy of Sciences achieved something extraordinary using a satellite called Mischius. They successfully entangled photons and transmitted them across a record-breaking distance of 1,200 kilometers, a feat that spanned entire cities, mountain ranges, and even the vacuum of space. Despite this vast separation, the entangled link held firm, surviving atmospheric interference and signal loss. This was no longer just a validation of Bell's theorem. It was a demonstration of quantum communication on a global scale. The experiment proved that entanglement could be sustained across immense distances, opening the door to future technologies such as quantum networks, entanglement-based encryption, and unhackable communication systems. These quantum links, immune to eavesdropping and perfectly synchronized, marked the dawn of a new era in communication technology, one that even Einstein himself could never have imagined. Then, in 2020, physicists took entanglement into an even stranger and more ambitious direction, scaling it up to macroscopic objects. Up to that point, entanglement had been observed in microscopic particles like photons, electrons, and single atoms. But what about larger systems? Could something visible, something that could be seen or touched, also be entangled? In a groundbreaking series of experiments, researchers managed to entangle macroscopic systems such as oscillating mirrors, vibrating crystals, and even clouds of atoms acting collectively. These systems involved trillions of particles moving in unison, yet they exhibited unmistakable quantum correlations. The implications were staggering. Entanglement wasn't confined to the invisible quantum realm. It could stretch into the tangible, macroscopic world. The line separating classical physics from quantum mechanics began to blur. If entanglement could occur between large, observable systems, it raised a profound question. Is the classical world we see around us merely an illusion, a decohered quantum web holding itself together at the edge of perception? Then, just a few years later, in 2023, scientists observed something once considered impossible: entanglement between top quarks at the Large Hadron Collider. These aren't stable, long-lived particles. Top quarks are among the heaviest and most unstable known, decaying in less than a trillionth of a second. And yet, even within that fleeting existence, the quarks managed to remain entangled. It was the highest energy demonstration of quantum entanglement ever recorded, confirming that entanglement is not a fragile lab anomaly. It's a universal property of matter and energy at all scales, from subatomic particles to cosmic structures. It's difficult to exaggerate the significance of this discovery. When Einstein and his colleagues wrote the EPR paper back in 1935, the very notion of manipulating or observing such phenomena was inconceivable. There were no satellites, no superconducting detectors, no quantum random number generators, not even the mathematical tools to describe many of the effects we now take for granted. Yet, less than a century later, humanity has not only verified the existence of quantum entanglement, but has begun to use it, to harness it in communication, computing, and perhaps even in our understanding of space-time itself. Still, every discovery has only deepened the mystery. If particles can remain connected across light years, what does that say about the fabric of the universe? Is space-time itself an emergent property of entanglement? Are black holes, wormholes, and gravity all linked to the same underlying quantum network? Could entanglement be not just a side effect of quantum theory, but the very foundation of physical reality? That brings us to the frontier of 2025, a year that has already reshaped what scientists thought they knew about quantum entanglement. Today, entanglement isn't just being observed, it's being engineered, manipulated, and designed for specific purposes. What once sounded like spooky action at a distance has now become one of the most powerful tools in modern physics. One of the year's most intriguing breakthroughs came from an unexpected area: gravity. For decades, physicists have struggled to unite quantum mechanics and Einstein's general relativity. Each theory works flawlessly in its own domain, one describing the world of the very small, the other governing the cosmos. But combining them has remained one of the greatest challenges in physics. In 2025, researchers at the Max Planck Institute made a major step toward bridging that gap. By placing entangled particles near massive rotating bodies, carefully controlled systems that simulated gravitational wells, the scientists detected subtle changes in entanglement fidelity depending on the local curvature of spacetime. In simpler terms, the strength and behavior of entanglement were influenced by gravity itself. The results hinted that the geometry of space could affect how quantum systems remain connected. This finding, while not definitive proof, supports an increasingly compelling hypothesis. Space-time itself may arise from quantum entanglement. The notion that the structure of reality, space and time, might emerge from hidden quantum correlations between particles is revolutionary. If true, it would mean that the universe isn't built from matter and energy sitting in space. Instead, space is built from entanglement. It's a concept that challenges everything we know, suggesting that what we experience as physical reality might be the shadow of a deeper quantum web. Meanwhile, across the Atlantic at MIT, another group of researchers made history by creating what they call entanglement microscopy, a technique that allows scientists to visualize entanglement directly at the microscopic scale. For decades, entanglement was something inferred through mathematical correlations or detector readings, never something seen or imaged. But through a clever use of quantum light sources and weak measurement techniques, the MIT team succeeded in capturing interference patterns that occur only when particles are entangled. The resulting images were haunting, shimmering, ghost-like fields representing non-local quantum structures that exist beyond ordinary perception. For the first time, scientists could see the fingerprints of entanglement. It was as if humanity had finally built a telescope for the quantum realm, a window into the invisible threads connecting the universe. But 2025 didn't stop at observation. Scientists also found new ways to create and control entanglement. One of the most exciting innovations came with a process known as total angular momentum entanglement. Traditionally, entanglement involved simple particle properties like spin or polarization. However, researchers at Nature Quantum Technology took it several steps further. They used laser-cooled atoms to link their entire angular momentum states, a combination of spin, orbital motion, and internal energy levels. This created an incredibly rich and stable form of entanglement, opening new avenues for quantum computing, sensing, and information transfer. In essence, we've entered an era where quantum entanglement is no longer a theoretical curiosity, it's a practical resource. From secure global communications to potential quantum gravity experiments, entanglement is transforming how we understand and interact with the universe. What began as an intellectual puzzle between Einstein and Bohr has become the foundation of a new technological revolution, and perhaps the key to understanding reality itself. Why does this matter? Because these multidimensional entangled states could form the foundation for the next generation of quantum processes, systems where each particle encodes an exponentially greater amount of information than ever before. It's like upgrading from simple Morse code to an entire orchestral symphony within a single atom. Then came the surprise no one expected: entanglement applied to strategy. In a collaboration between quantum physicists and game theorists at Oxford University and the University of Tokyo, researchers discovered that entanglement could create measurable advantages in competitive decision-making. By running a quantum version of the prisoner's dilemma, they found that agents using entangled qubits achieved cooperative outcomes that surpassed every classical strategy. This wasn't just theoretical speculation. The team used real entangled qubits to simulate how information could be shared or concealed across interconnected quantum systems that were effectively playing against one another. The outcome marked the birth of a new field, quantum game theory. In this framework, entanglement reshapes how strategy, probability, and communication function. It's a first glimpse of a future where economics, negotiation systems, and artificial intelligence may evolve beyond classical limits, where outcomes aren't determined by linear logic, but by quantum relationships that defy predictability. But perhaps the most remarkable experiment of the year came not from a massive research facility, but from a small, determined lab in Switzerland. There, physicists accomplished something unprecedented. They entangled entire molecules, not single atoms or photons, but complex organic molecules containing thousands of particles. Using precisely tuned magnetic fields and specially designed optical traps, They brought two separate molecules into quantum entanglement and confirmed it through correlated spectroscopic measurements. This was far more than a scientific novelty. Molecules represent the next great scale of quantum control, a step toward molecular-scale quantum devices capable of performing computations, sensing changes, or transmitting signals at the level of nature's own building blocks. These findings opened a path to a new generation of quantum sensors and processors, machines not built from silicon and metal, but from entangled molecular systems. Across all these breakthroughs, one message stands out clearly. Humanity is no longer merely observing entanglement. We are learning to use it, to control it, to engineer it. While it remains unpredictable and fragile, it's no longer an untamable mystery. It has become a practical tool, powerful enough to build machines, transmit information, test the boundaries of physics, and reshape our understanding of connection and reality itself. This moment in history is strikingly similar to the early days of electricity. At first, electricity was unseen, misunderstood, even frightening. Then it became a novelty, then a utility, and eventually the very foundation of modern civilization. Quantum entanglement may follow the same path. What was once dismissed as a strange, ghostly phenomenon might soon become the engine driving the technologies of the future. Of course, as always, progress raises as many questions as it answers. If entanglement can stretch across vast distances and scales, if it can be measured, manipulated, and trusted to store and transmit information, what else might it be capable of? Could we someday entangle biological systems, neurons, proteins, even living cells? Some fringe theories have even speculated about quantum links in human consciousness, though such claims remain unverified. Still, the direction of progress is unmistakable. By 2025, one thing has become absolutely clear. Entanglement is no longer a philosophical oddity. It is now a scientific tool, a technological principle, and perhaps even a physical force, something that can be measured, mapped, and ultimately mastered. And as the focus shifts from research to application, we find ourselves standing at the threshold of a quantum revolution, where entanglement is not just an abstract concept to admire, but the driving mechanism of a new technological era. If the 20th century was defined by the digital revolution, the 21st century will likely be remembered for something far more profound, more complex, and infinitely more powerful. At the core of this new age lies quantum entanglement, a phenomenon that challenges everything we thought we knew about information, computation, and reality itself. To grasp how entanglement fuels this next wave of progress, we have to first let go of our dependence on classical logic. Traditional computers, your phone, your laptop, even the world's fastest supercomputers, operate on bits, binary units of information that exist as either 0 or 1, on or off. These bits follow strict, predictable logic gates. Every calculation, no matter how complex, boils down to long chains of these binary decisions. Quantum computers, however, operate on qubits. Quantum bits that can exist in multiple states at once, thanks to a principle known as superposition. But superposition alone isn't what gives them their extraordinary power. That power comes from entanglement. When qubits become entangled, their states are no longer independent. The condition of one instantly influences the other, no matter how far apart they are. This interconnection allows for a kind of computational parallelism that classical computers can't replicate. Imagine trying to find one specific page in an endless library. A classical computer would search one book at a time, page by page. A quantum computer powered by entanglement can effectively analyze all pages simultaneously, not through speed, but through a deep structural web of probability and correlation that narrows down solutions in ways the classical world cannot match. Take Shor's algorithm, for example. It can factor extremely large numbers exponentially faster than any classical algorithm, a breakthrough with direct implications for encryption. Today's digital security, protecting banks, governments, and global communication, relies on the difficulty of factoring large primes. Shor's algorithm, powered by entangled qubits, can shatter that assumption. Without entanglement, the algorithm wouldn't work. It's the quantum linkage between qubits that allows them to explore and compare countless possibilities at once. Similarly, Grover's algorithm revolutionizes how we search unstructured data. While classical systems examine each entry one by one, Grover's quantum algorithm leverages entanglement to amplify correct answers and suppress incorrect ones, achieving a kind of resonant computation that cuts through complexity in a fraction of the time. And this is no longer hypothetical. Companies like IBM, Google, and D-Wave are already constructing operational quantum processors. In 2019, Google announced that it had achieved quantum supremacy, the moment when a quantum processor performs a task no classical computer can complete within a reasonable time frame. The processor responsible used dozens of entangled superconducting qubits, kept near absolute zero to maintain stability. Still, this technology is in its infancy. Quantum computers are incredibly sensitive. The smallest vibration, magnetic field, or thermal fluctuation can break their delicate entanglement, a problem known as decoherence. Maintaining long-lived large-scale entanglement is one of the greatest engineering challenges of the modern era. That's why quantum error correction has become a critical field of study. In classical systems, bits can simply be copied and checked for mistakes. But quantum information cannot be copied directly. The no-cloning theorem forbids it. So instead, scientists use entangled networks of qubits to detect and correct errors without destroying the quantum information they're meant to preserve. It's like fixing a bomb's wiring without ever opening the casing, using correlations alone to infer what's wrong and correct it in real time. The potential rewards are monumental. Quantum computers could simulate molecular interactions too complex for any traditional machine, revolutionizing material science and drug discovery. They could optimize global logistics, design new chemical reactions, and decrypt codes previously considered unbreakable. Behind all of it lies entanglement, the invisible framework that makes these miracles possible. But computation is just one part of the story. Entanglement's power also extends to communication and cryptography. In quantum cryptography, it enables a level of security that's not just hard to hack, it's physically impossible to compromise. Consider quantum key distribution QKD. In this system, two users, commonly referred to as Alice and Bob, exchange entangled photons to establish a secure encryption key. Because of the fundamental rules of quantum mechanics, any attempt by a third party, Eve, to eavesdrop on the communication disturbs the entanglement itself, immediately revealing the intrusion. Unlike traditional encryption methods, which rely on mathematical difficulty, QKD relies on physics itself. If someone tries to intercept the transmission, the entangled photons collapse, and both participants instantly know that security has been breached. This isn't a theoretical idea. It's already being tested and implemented in real-world communication networks, even across satellite links. Quantum entanglement, once considered a paradox, is now the foundation of the next technological age, an era where computation, communication, and reality itself are intertwined in ways we are only beginning to understand. Local realism is the idea that physical properties exist independently of observation, realism, and that no influence can travel faster than light, locality. For centuries, this was the foundation of classical physics, the bedrock of our intuition about cause and effect. But quantum mechanics shattered this comfort zone. Entanglement suggests that when two particles are linked, their properties are not defined independently, but exist in a shared, unified state until one is measured. The instant one is observed, the other's outcome is set, regardless of distance. This correlation doesn't transmit energy or information faster than light, yet it still happens instantaneously. The implications are staggering. Either reality is non-local, or measurement outcomes do not exist until observed, or both. This leads us into the heart of the quantum interpretation wars. The Copenhagen interpretation, championed by Niels Bohr, argues that particles have no definite state until measured. that observation itself collapses the wave function into a particular outcome. Reality in this view is not fully real until observed. Einstein found this unacceptable, famously asking, "Do you really believe the moon isn't there when you're not looking at it?" But quantum experiments seem to side with Bohr. The act of measurement defines the state, not the other way around. Then came the many-worlds interpretation, proposed by Hugh Everett in 1957. It sidesteps the problem of collapse entirely. In this view, when an entangled system is measured, the universe splits into multiple parallel branches, one for each possible outcome. Every result exists somewhere, just in different universes. There's no spooky action, no collapse, just an ever-expanding web of realities, each as real as the next. It's an elegant idea, but also unsettling. If true, every decision, every quantum event spawns countless new worlds, infinite versions of reality, all unfolding simultaneously. Others take a different approach. The pilot wave theory, originally proposed by Louis de Broglie and later developed by David Bohm, restores determinism to quantum mechanics. It suggests that particles do have definite positions and trajectories, guided by an underlying quantum potential, a hidden wave that connects all things. In this model, entanglement arises from the deep, non-local nature of this pilot wave. Reality is not random but coordinated through a universal field beneath the surface. Though elegant, this idea introduces its own puzzles, particularly how such a non-local mechanism could coexist with relativity. And then there's the relational interpretation, a radical but increasingly discussed perspective. It argues that quantum states don't describe an objective reality, but only relationships between systems. In this sense, entanglement doesn't connect particles directly, it connects the information they share. Reality itself may be a web of correlations, not an assembly of independent objects. Nothing exists in isolation. Everything exists through interaction. But if this is true, what does that mean for us? For consciousness, for free will, for the very idea of separateness? Some thinkers have taken these implications further, suggesting that entanglement might underlie not just particles but the structure of space-time, that what we call space is itself an emergent property of quantum connections. Others go even further, wondering whether entanglement plays a role in cognition, in how the brain processes information, or even how awareness arises. While such claims remain speculative, they echo a larger philosophical shift from a universe made of things to a universe made of relations. The truth is, entanglement forces us to rethink reality from the ground up. If distance is not an obstacle, if separation is an illusion, then our classical picture of the universe as a collection of discrete parts might be incomplete. Instead, reality could be a single, holistic entity, interconnected at every level, from quarks to galaxies. What we perceive as individuality may simply be a local perspective within a vast entangled whole. As quantum technologies evolve, from computers and sensors to secure communication and teleportation, they're not just reshaping engineering, they're reshaping philosophy. The more we learn to use entanglement, the more we must ask what it really is. A tool, a feature of information, or the deep structure of existence itself? And perhaps that's where the story of entanglement leaves us, suspended between science and mystery. Every experiment confirms its reality, every application deepens its power. Yet, the more we understand, the less certain we are about what understanding even means. In the end, entanglement is more than a phenomenon. It's a reminder that the universe is not what it seems, that beneath the surface of matter and measurement lies a hidden order, a unity that binds everything together. So when we look at the night sky and see distant stars, we might remember the photons reaching our eyes are not alone. Somewhere, somehow, they remain connected to what they once were part of. Perhaps the same is true for us. Like the particles that built us, we too might be entangled, not just with each other, but with the universe itself. Local realism argues that particles have definite properties that exist independently of observation. That's realism, and that no information or influence can move faster than the speed of light. That's locality. But John Bell demonstrated mathematically and conclusively that any theory obeying both these principles fails to reproduce the predictions of quantum mechanics. The universe, as it turns out, refuses to honor both simultaneously. A choice must be made, and most physicists have chosen to abandon realism. Letting go of realism means accepting that particles do not possess fixed attributes until they are measured. Reality, then, isn't a static set of independent facts waiting to be discovered, but rather a network of probabilities that solidify only upon observation. Niels Bohr fully embraced this uncertainty. According to the Copenhagen interpretation, measurement doesn't just reveal what is real, it creates it. Entanglement, in this sense, isn't a signal passing between particles, but a shared destiny. Two particles linked by a common wave function that collapses together only when observed. However, not everyone accepted this explanation. In 1957, Hugh Everett proposed the many worlds interpretation, an idea that radically reshaped the discussion. It suggests that every possible outcome of a quantum event actually happens in separate branching universes. When you measure one of an entangled pair, you don't pick a single outcome. Instead, the universe splits. One version of you sees spin up, another sees spin down. In this view, entanglement acts as a bridge between these branching realities, a silent witness to the moment when worlds diverge. Another alternative is the pilot wave theory, also known as Bohmian mechanics. It attempts to restore realism, but at the cost of breaking locality. It introduces hidden, non-local variables that guide particles through a deterministic quantum landscape, like boats drifting along an invisible current. Here, the pilot wave determines the outcome with certainty, but does so by allowing influences that travel faster than light. Once again, we're forced to sacrifice one fundamental assumption to preserve another. Even more mind-bending are interpretations rooted in information theory. These propose that reality itself may not be made of matter at all, but of information. That everything we perceive is the result of correlations between data points within a vast cosmic computation. In this perspective, space and time don't pre-exist. They emerge from the web of entanglement, much like pixels forming an image on a digital screen. This idea is sometimes described through the it-from-qubit hypothesis, explored by physicists such as John Preskill and Seth Lloyd. They argue that entanglement is not merely a property of the universe, it may be its source. And that leads to perhaps the most unsettling question of all. If reality is information, who or what is performing the computation? Entanglement also challenges our understanding of free will. In loophole-free Bell tests, experimenters must ensure that the choice of measurement settings is made independently, free of any hidden correlation with the particles being measured. But if everything in the universe, including those experimental decisions, is entangled at some deeper level, then true independence might be an illusion. Are we genuinely making choices, or are we merely acting out correlations encoded long ago in the quantum fabric of reality? These questions are far from philosophical curiosities. They strike at the heart of how we understand consciousness, causality, and even time itself. Because entanglement seems to operate outside of time, it doesn't matter whether particles once interacted or have always been apart. Their connection transcends both distance and duration. Some physicists now suggest that time itself might emerge from entanglement, just as space does. The Page-Wouters mechanism proposes that time is not a universal clock ticking forward, but a property that arises from correlations between entangled systems. There is no absolute now, only relationships between quantum states. If that's true, then the arrow of time, the sense of past giving way to future, may be nothing more than an illusion created by the process of decoherence, as entangled systems lose their quantum nature and become classical. And that brings us full circle. Decoherence is the process by which entangled systems interact with their environment and lose their quantum behavior, giving rise to the familiar classical world we experience. The entanglement doesn't vanish. It becomes hidden, buried beneath countless interactions with surrounding particles. But some researchers believe that if we could isolate quantum systems perfectly and preserve their entanglement long enough, we might peer beneath this classical disguise and glimpse the true quantum nature of reality. For those raised on the intuitions of Newton and Einstein, this isn't just a scientific puzzle, it's a philosophical reckoning. Entanglement challenges the belief that the universe is built from independent objects governed by cause and effect. Instead, it implies that the cosmos is made of relationships, an intricate web of interdependent possibilities that only become real when observed. Yet beyond the metaphysical wonder lies a more practical question. How do we use this strange phenomenon? How do we move from the realm of thought experiments to real-world applications? Scientists are now learning how to engineer entanglement, to stabilize and harness it for technologies that could reshape communication, computation, and security. But that's no easy task. Entanglement is fragile, easily destroyed by noise, heat, or even the faintest environmental disturbance. A stray vibration, an errant photon, or a trace of background radiation can unravel it completely. That's why modern quantum machines must operate under extreme conditions, near absolute zero, within magnetic vacuums or in total isolation, just to keep entanglement alive. And even when preserved, scalability remains an immense challenge. A single entangled pair is remarkable, a dozen is groundbreaking. But to build practical quantum computers or global quantum networks, we need thousands, perhaps millions, of entangled qubits working together while maintaining coherence long enough to perform meaningful computations. This is where quantum error correction becomes essential. Since quantum data cannot be copied in the classical sense, error correction relies on spreading information across multiple qubits through entanglement itself. This allows the system to detect and fix errors without directly measuring or collapsing the quantum state. A digital immune system for entanglement. However, error correction alone won't solve every problem. Researchers are experimenting with new materials and architectures, such as topological qubits, which store information in the shape of their collective quantum fields rather than individual particle states. These quantum knots are inherently more stable, resisting noise and holding entanglement for longer periods. Other teams use trapped ions, photonic circuits, or neutral atoms suspended in light fields, each approach offering trade-offs between speed, stability, and scalability. Yet all share the same goal: to tame entanglement just enough to build with it. Another major obstacle is distribution. Creating entanglement in a lab is one thing. Sharing it across cities, continents, or even between Earth and satellites is another. Quantum communication requires sending entangled photons through optical fibers or open space, but over long distances they're easily scattered or absorbed. To solve this, scientists are developing quantum repeaters, devices that extend entanglement without violating the no-cloning theorem. These repeaters act as relay stations, storing and refreshing entanglement across multiple links, much like pit stops in a marathon. The ultimate dream is a global quantum internet, where entanglement can be distributed on demand anywhere on Earth. That dream took a major step forward in 2025, when European and Japanese researchers successfully entangled quantum nodes 600 kilometers apart using a combination of ground-based fiber and satellite relays. The breakthrough relied on entanglement swapping, a technique that allows two previously separate systems to become entangled by interacting through parts of another entangled pair. This ability to extend entanglement through intermediary nodes is the foundation of any future quantum network, one that could someday revolutionize how we process and transmit information, bringing the strangest law of nature out of theory and into technology. Local realism argues that particles have definite properties that exist independently of observation, That's realism, and that no information or influence can move faster than the speed of light. That's locality. But John Bell demonstrated mathematically and conclusively that any theory obeying both these principles fails to reproduce the predictions of quantum mechanics. The universe, as it turns out, refuses to honor both simultaneously. A choice must be made, and most physicists have chosen to abandon realism. Letting go of realism means accepting that particles do not possess fixed attributes until they are measured. Reality, then, isn't a static set of independent facts waiting to be discovered, but rather a network of probabilities that solidify only upon observation. Niels Bohr fully embraced this uncertainty. According to the Copenhagen interpretation, measurement doesn't just reveal what is real, it creates it. Entanglement, in this sense, isn't a signal passing between particles, but a shared destiny. Two particles linked by a common wave function that collapses together only when observed. However, not everyone accepted this explanation. In 1957, Hugh Everett proposed the many worlds interpretation, an idea that radically reshaped the discussion. It suggests that every possible outcome of a quantum event actually happens in separate branching universes. When you measure one of an entangled pair, you don't pick a single outcome. Instead, the universe splits. One version of you sees spin up, another sees spin down. In this view, entanglement acts as a bridge between these branching realities, a silent witness to the moment when worlds diverge. Another alternative is the pilot wave theory, also known as Bohmian mechanics. It attempts to restore realism, but at the cost of breaking locality. It introduces hidden, non-local variables that guide particles through a deterministic quantum landscape, like boats drifting along an invisible current. Here, the pilot wave determines the outcome with certainty, but does so by allowing influences that travel faster than light. Once again, we're forced to sacrifice one fundamental assumption to preserve another. Even more mind-bending are interpretations rooted in information theory. These propose that reality itself may not be made of matter at all, but of information, that everything we perceive is the result of correlations between data points within a vast cosmic computation. In this perspective, space and time don't pre-exist. They emerge from the web of entanglement, much like pixels forming an image on a digital screen. This idea is sometimes described through the "it from qubit" hypothesis, explored by physicists such as John Preskill and Seth Lloyd. They argue that entanglement is not merely a property of the universe, it may be its source. And that leads to perhaps the most unsettling question of all. If reality is information, who or what is performing the computation? Entanglement also challenges our understanding of free will. In loophole-free Bell tests, experimenters must ensure that the choice of measurement settings is made independently, free of any hidden correlation with the particles being measured. But if everything in the universe, including those experimental decisions, is entangled at some deeper level, then true independence might be an illusion. Are we genuinely making choices, or are we merely acting out correlations encoded long ago in the quantum fabric of reality? These questions are far from philosophical curiosities. They strike at the heart of how we understand consciousness, causality, and even time itself. Because entanglement seems to operate outside of time. It doesn't matter whether particles once interacted or have always been apart. Their connection transcends both distance and duration. Some physicists now suggest that time itself might emerge from entanglement, just as space does. The Page-Wouters mechanism proposes that time is not a universal clock ticking forward, but a property that arises from correlations between entangled systems. There is no absolute now, only relationships between quantum states. If that's true, then the arrow of time, the sense of past giving way to future, may be nothing more than an illusion created by the process of decoherence, as entangled systems lose their quantum nature and become classical, and that brings us full circle. Decoherence is the process by which entangled systems interact with their environment and lose their quantum behavior, giving rise to the familiar classical world we experience. The entanglement doesn't vanish. It becomes hidden, buried beneath countless interactions with surrounding particles. But some researchers believe that if we could isolate quantum systems perfectly and preserve their entanglement long enough, we might peer beneath this classical disguise and glimpse the true quantum nature of reality. For those raised on the intuitions of Newton and Einstein, this isn't just a scientific puzzle, it's a philosophical reckoning. Entanglement challenges the belief that the universe is built from independent objects governed by cause and effect. Instead, it implies that the cosmos is made of relationships, an intricate web of interdependent possibilities that only become real when observed. Yet beyond the metaphysical wonder lies a more practical question. How do we use this strange phenomenon? How do we move from the realm of thought experiments to real-world applications? Scientists are now learning how to engineer entanglement, to stabilize and harness it for technologies that could reshape communication, computation, and security. But that's no easy task. Entanglement is fragile, easily destroyed by noise, heat, or even the faintest environmental disturbance. A stray vibration, an errant photon, or a trace of background radiation can unravel it completely. That's why modern quantum machines must operate under extreme conditions, near absolute zero, within magnetic vacuums, or in total isolation, just to keep entanglement alive. And even when preserved, scalability remains an immense challenge. A single entangled pair is remarkable, a dozen is groundbreaking. But to build practical quantum computers or global quantum networks, we need thousands, perhaps millions, of entangled qubits working together while maintaining coherence long enough to perform meaningful computations. This is where quantum error correction becomes essential. Since quantum data cannot be copied in the classical sense, error correction relies on spreading information across multiple qubits through entanglement itself. This allows the system to detect and fix errors without directly measuring or collapsing the quantum state, a digital immune system for entanglement. However, error correction alone won't solve every problem. Researchers are experimenting with new materials and architectures, such as topological qubits, which store information in the shape of their collective quantum fields rather than individual particle states. These quantum knots are inherently more stable, resisting noise and holding entanglement for longer periods. Other teams use trapped ions, photonic circuits, or neutral atoms suspended in light fields, each approach offering trade-offs between speed, stability, and scalability. Yet all share the same goal: to tame entanglement just enough to build with it. Another major obstacle is distribution. Creating entanglement in a lab is one thing, sharing it across cities, continents, or even between Earth and satellites is another. Quantum communication requires sending entangled photons through optical fibers or open space, but over long distances, they're easily scattered or absorbed. To solve this, scientists are developing quantum repeaters, devices that extend entanglement without violating the no-cloning theorem. These repeaters act as relay stations, storing and refreshing entanglement across multiple links, much like pit stops in a marathon. The ultimate dream is a global quantum internet, where entanglement can be distributed on demand anywhere on Earth. That dream took a major step forward in 2025, when European and Japanese researchers successfully entangled quantum nodes 600 kilometers apart, using a combination of ground-based fiber and satellite relays. The breakthrough relied on entanglement swapping, a technique that allows two previously separate systems to become entangled by interacting through parts of another entangled pair. This ability to extend entanglement through intermediary nodes is the foundation of any future quantum network, one that could someday revolutionize how we process and transmit information, bringing the strangest law of nature out of theory and into technology. Local realism suggests that particles have definite properties that exist independently of observation. This is called realism, and that no information or influence can travel faster than light. This is known as locality. However,
John Bell proved mathematically that any theory adhering to both these principles fails to reproduce the predictions of quantum mechanics. In short, the universe doesn't obey both. We have to choose, and most physicists have chosen to let go of realism.
This means that particles don't have fixed states until they are measured. Reality, then, isn't a collection of predetermined facts waiting to be discovered, but a web of probabilities that only become real when observed. Niels Bohr accepted this uncertainty through the Copenhagen interpretation, which claims that measurement doesn't just reveal reality, it creates it. In this view, entanglement isn't about sending signals between particles, it's about a shared fate. Two particles connected by a common wave function collapse together only when observed, but not everyone accepted this explanation. In 1957, Hugh Everett proposed the many worlds interpretation, a radical idea that suggests every possible outcome of a quantum event actually happens, but in separate branching universes. When we measure an entangled pair, we don't choose a single outcome. The universe itself splits. One version of you sees spin up, another sees spin down. Entanglement, in this scenario, is a link between branching realities, silently marking the point where worlds diverge. Another interpretation, called the pilot wave theory or Bohmian mechanics, restores realism but sacrifices locality. It introduces hidden non-local variables that guide particles in a deterministic way, like boats following an invisible quantum current. In this theory, the pilot wave determines every outcome precisely, but it does so by allowing faster-than-light effects, breaking one of the most fundamental principles of relativity. Even more intriguing are theories based on information, suggesting that reality itself might be made not of matter, but of information. According to this idea, everything we perceive is the result of correlations between data points in a vast computational structure. Space and time in this framework don't exist on their own. They emerge from the patterns of entanglement, like pixels forming a digital image. The it-from-qubit hypothesis, proposed by physicists John Preskill and Seth Lloyd, suggests that entanglement isn't just a part of the universe, it might be its very foundation. And that leads to one haunting question. If reality is information, who or what is doing the computing? Entanglement also challenges the idea of free will. In loophole-free Bell tests, the settings for measurement must be chosen independently of the particle properties being tested. But if everything in the universe, including those choices, is entangled at some deep level, then maybe true independence doesn't exist. Are our choices genuine, or just outcomes of correlations encoded long ago in the quantum fabric of reality? These are not abstract philosophical riddles. They touch everything, from consciousness to causality, even the nature of time itself. Entanglement seems to ignore time. It doesn't care whether particles were once connected or have always been apart. Their link transcends both space and duration. Some researchers now believe that time might itself emerge from entanglement. The Page-Wooter's mechanism suggests that time is not a universal clock ticking forward, but a property that arises from correlations between quantum systems. There is no single flow of time, just relationships between quantum states. If this is true, the arrow of time, the sense of past and future, might simply be an illusion created by decoherence, as entangled systems lose their quantum behavior and become classical. That brings us back to the concept of decoherence, the process by which quantum systems interact with their surroundings and lose their entanglement. This is what gives rise to the classical world we see. The entanglement doesn't vanish. It just becomes buried beneath countless interactions with the environment. But some scientists believe that if we could isolate quantum systems long enough, we could glimpse the true quantum face of reality beneath this classical mask. For those raised on Newton and Einstein, this isn't just a scientific revelation, it's a philosophical shift. Entanglement challenges the notion that the universe is made of independent objects governed by cause and effect. It suggests instead that the universe is made of relationships, that nothing exists in true isolation, and that everything is bound together in a web of interdependent possibilities. But moving from philosophy to practice brings new challenges. How do we actually use this fragile, elusive phenomenon? How do we transform entanglement from an idea into a working technology? Scientists around the world are now learning to control and harness entanglement for real-world applications in computing, communication, and encryption. Yet this is no simple task. Entanglement is extremely fragile. It breaks at the slightest disturbance. A small vibration, a stray photon, or even background radiation can destroy it. This is why most quantum computers operate near absolute zero or in near-perfect vacuum chambers, to keep entanglement alive for as long as possible. Even then, scalability remains the greatest obstacle. A single entangled pair is impressive. A dozen is extraordinary. But building practical quantum computers or global quantum networks requires thousands, even millions, of entangled qubits working together and staying coherent long enough to perform meaningful computations. This is where quantum error correction becomes essential. Since quantum data cannot be copied directly, error correction spreads information across multiple qubits through entanglement itself. If one qubit is disturbed, the others can detect and correct the error without collapsing the system, a kind of digital immune system for quantum data. Still, error correction alone isn't enough. Scientists are exploring new architectures like topological qubits, which store information not in individual particles, but in the shapes of their quantum fields. These systems, sometimes called quantum knots, are far more resistant to noise and can preserve entanglement for longer durations. Other teams are working with trapped ions, photonic circuits, and neutral atoms suspended in light fields. Each method has its trade-offs between stability, speed, and scalability, but all share a single goal: taming entanglement so it can be used. Another critical challenge is distribution. Creating entanglement inside a lab is one thing, sharing it over long distances is another. Quantum communication involves transmitting entangled photons through fiber optics or open air, but along the way they can be absorbed, scattered, or decohere completely. To overcome this, scientists are developing quantum repeaters, devices that extend entanglement over vast distances without breaking the no-cloning rule. These act like relay stations, briefly storing and refreshing entanglement before passing it onward, similar to pit stops in a race. This ability to relay entanglement through intermediate nodes is the foundation for any large-scale quantum network. It represents humanity's growing ability to take one of nature's strangest, most fragile phenomena and turn it into a tool that could redefine the future of technology and perhaps our understanding of reality itself. Entanglement isn't just real. It might be the most real thing in the entire universe. If it can shape space-time, influence information, and lie at the heart of black holes, then surely it must belong to the cold and distant realm of physics. But what if it's closer than that? What if entanglement doesn't exist only in vacuum chambers or particle colliders, but also within us, in the chemistry of our cells, in the reactions that occur in our brains, and perhaps even in the very origin of life itself? Over the past few decades, an emerging discipline known as quantum biology has begun to explore that possibility. Its premise is simple yet revolutionary, that quantum effects, particularly entanglement, may play a crucial role in biological systems. Long dismissed as too fragile to survive the warm, chaotic environments of living organisms, entanglement may in fact be robust and purposeful enough to persist, influencing molecular behavior in ways we're only beginning to understand. Consider enzymes, the biological catalysts that make life possible by accelerating chemical reactions by factors of trillions. Classical biochemistry explains much of how they work, but not everything. Some enzymes facilitate reactions that shouldn't happen at all under classical physics, moving particles like protons and electrons across energy barriers without sufficient energy. The explanation lies in quantum tunneling, a process governed by the same wave function dynamics that give rise to entanglement itself. But tunneling doesn't tell the whole story. In 2022, researchers at Oxford proposed that entangled vibrational states within enzymes might allow for precise control of chemical bond geometries. In other words, enzymes could be using quantum correlations to direct reactions far more efficiently than random thermal motion ever could. The enzyme isn't just shaking molecules into place. It knows, in a strange quantum sense, exactly when and where to act. An even stronger case for biological entanglement emerges from photosynthesis. Plants and bacteria convert sunlight into energy with near-perfect efficiency, something that defies classical explanation. Experiments using ultrafast laser pulses revealed that when photons strike pigment protein complexes, the resulting energy doesn't simply move randomly. Instead, it travels through multiple pathways simultaneously in a quantum superposition. Within these energy transfer pathways, scientists have found signs of entanglement, fleeting but measurable, helping direct the energy toward the reaction center with extraordinary precision. This isn't speculation. In 2020, experiments using entangled photon spectroscopy directly probed these biological systems and confirmed that pigment molecules maintain quantum correlations longer than expected, even at body temperature. It's as though evolution discovered a quantum algorithm, not built in silicon, but in chlorophyll. Then there's the mystery of olfaction, our sense of smell. For decades, the dominant theory was shape-based, that odor molecules fit into receptors like keys into locks. But that model fails to explain how molecules with nearly identical shapes can produce completely different smells. An alternative theory, first suggested by Luca Turin, proposes that our noses detect molecular vibrations via quantum tunneling, distinguishing scents by how electrons leap across molecules. Recent research indicates that entanglement between molecular states could amplify this effect, making smell less like touch and more like a quantum form of hearing.
Perhaps the most provocative implications of quantum biology arise in genetics. Processes like DNA replication, protein folding, and gene expression operate with astonishing accuracy, yet are constantly threatened by random noise. Some scientists believe that quantum coherence may help maintain that precision. In 2025, researchers at MIT discovered signatures of quantum entanglement in simulations of DNA base pair reading. Their findings suggest that quantum correlations might help reduce transcription errors during cell replication, effectively acting as an error correction mechanism in the genetic code.
This raises a profound question. Could entanglement have been essential to the origin of life itself? Some theories of abiogenesis, the process by which life first emerged from non-living matter, now propose that conditions on early Earth may have allowed entangled molecular systems to form spontaneously. These systems could have coordinated behaviors across time and space, promoting stability and self-organization in prebiotic chemistry. In this view, entanglement wasn't a byproduct of life. It was the spark that started it. It allowed non-living molecules to interact coherently, paving the way for complexity, self-replication, and ultimately, biology. One bold hypothesis put forward by physicist Jim Al-Khalili and biologist John Joe McFadden goes even further. They propose that evolution itself might have quantum roots, that mutations in DNA, usually considered random, might sometimes follow coherent quantum pathways. This doesn't imply purpose or design, but rather that entanglement shapes probability, guiding evolution in subtle ways by influencing which molecular outcomes are most likely to occur. And inevitably, this brings us to perhaps the deepest mystery of all: consciousness. How do electrical impulses and chemical gradients in the brain give rise to the vivid inner world of subjective experience? Some researchers believe that entanglement may hold the key. The Penrose-Hameroff-Ork-OR theory proposes that consciousness arises from quantum processes occurring inside microtubules, structural filaments within neurons. These microtubules may host entangled quantum states that can maintain coherence for surprisingly long periods. potentially linking neural activity into unified conscious awareness. If true, this would mean that entanglement doesn't just connect distant particles, it might connect the very thoughts in our minds. It would suggest that life, awareness, and even the experience of being human are not exceptions to the universe's quantum nature, but direct expressions of it. Entanglement, once thought to belong only to the strange world of physics, might instead be the thread weaving together existence itself, from the first spark of life to the light in our eyes, from the chemistry of cells to the consciousness that perceives it all. So, how do we even begin to understand this mysterious thing called quantum entanglement? It sounds like pure science fiction, something out of a fantasy novel, yet it's one of the most mathematically confirmed and experimentally verified phenomena in physics. To grasp what it truly represents and why it could be the most crucial key to understanding reality itself, we first have to clear away a few misconceptions. Picture this: two particles born together in a single quantum event. Measurement is what collapses a quantum wave function, that invisible cloud of probabilities, into one definite result. It's like tossing a coin that exists in a blur of both heads and tails until the moment you look at it. Only when you observe it does it choose a side. Now, here's where the real mystery begins. When two particles become entangled, their wave functions merge into one shared state, a unified mathematical description of the entire system. You can't talk about one particle without talking about the other, no matter how far apart they are. Entangled particles don't behave like two separate entities. They act like one continuous object spread across space. For example, if you measure the spin of one electron and find it pointing up, the spin of its entangled twin will always point down. Not because one influenced the other, but because both results were encoded in a shared quantum reality from the start. The universe doesn't decide which spin is up or down until one is measured, but the moment that measurement happens, the partner particle's state is instantly determined, even across cosmic distances. Einstein couldn't stand this idea. To him, it implied that information was traveling faster than light. Or worse, that particles had no definite properties until someone looked at them. He dismissed this as nonsense, famously calling it spooky action at a distance. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published the EPR paper, the Einstein-Podolsky-Rosen paradox, arguing that quantum mechanics must be incomplete. They suggested that hidden variables, unknown to us, might determine outcomes behind the scenes. If such variables existed, the universe could remain local and predictable without resorting to spooky non-locality. But Niels Bohr and the broader quantum community disagreed. Bohr insisted that Einstein had misunderstood the nature of reality at the quantum level. Quantum mechanics wasn't incomplete. It was simply describing a reality different from anything classical physics could imagine. Asking for a particle's state before it's measured, Bohr argued, was like asking the color of a sound. The question itself doesn't make sense. In this view, reality isn't something that exists independently of observation. It's something shaped or even defined by it. Entanglement, as strange as it seems, isn't just real. It might be the most fundamental aspect of the universe. If it can influence space-time, carry information, and even explain black holes, why stop there? What if entanglement isn't just something that happens in vacuum chambers or high-energy colliders, but something that operates inside us, within the chemistry of our cells, our neural processes, and maybe even the origins of life itself? Enter quantum biology, an emerging field suggesting that quantum effects, including entanglement, could play vital roles in biological systems. For decades, scientists believed quantum phenomena were too fragile to survive in the warm, noisy environment of living cells. But evidence now suggests the opposite, that life may have evolved to use these effects. Take enzymes, the biological catalysts that make life possible by speeding up reactions trillions of times. Classical chemistry explains much of their work, but not all. Some enzymes pull off reactions that should be impossible under traditional physics, moving electrons or protons across barriers without enough energy. The likely explanation: quantum tunneling, where particles pass through barriers due to their wave-like nature, a process linked directly to entanglement. In 2020, using entangled photon spectroscopy, scientists directly measured these quantum correlations, showing that pigment molecules maintain coherence longer than anyone expected, even at body temperature. It's almost as if evolution discovered its own quantum algorithm, written not in silicon but in chlorophyll. Then there's olfaction, the sense of smell. For decades, scientists thought smell worked like a lock-and-key mechanism. Molecules fit into receptors matching their shape. But that model can't explain why some molecules with nearly identical shapes smell completely different. In the 1990s, Luca Turin proposed a radical alternative, that our noses detect molecular vibrations through quantum tunneling, allowing us to hear the vibration frequencies of molecules. Some researchers now suggest that entanglement between molecular states may amplify this effect, making smell less about shape and more about quantum resonance. Even genetics might be influenced by entanglement. DNA replication, protein folding, and gene expression require exquisite precision despite constant thermal noise. In 2025, researchers at MIT found entanglement-like correlations in DNA base pair simulations, suggesting that quantum effects may help prevent transcription errors during replication. Some theories of abiogenesis, the origin of life, even propose that entangled molecular systems on early Earth might have self-organized into living structures, making entanglement not a byproduct of life, but its trigger. Physicist Jim Al-Khalili and biologist John Joe McFadden have gone even further, proposing that evolution itself may have quantum roots, that mutations in DNA may sometimes follow coherent quantum pathways, guided not by pure randomness, but by structured quantum probability. This doesn't mean there's intent or consciousness behind evolution, but it does hint at a hidden quantum architecture shaping life's possibilities. And that brings us to the most controversial question of all: consciousness. How do electrical impulses in the brain translate into thoughts, emotions, and awareness? The Penrose-Hameroff-Orr theory suggests that consciousness might emerge from quantum processes inside microtubules, microscopic structures in neurons that could host entangled states, maintaining coherence for surprising durations. Though highly debated, the idea gained new traction in 2023 when experiments at the Max Planck Institute detected entangled spin states in cytoskeletal proteins, showing that biological systems might preserve quantum information under the right conditions. If true, this could explain how distant parts of the brain synchronize instantly, or how awareness emerges from a web of separate but connected neurons. Skepticism remains warranted. The brain is chaotic, noisy, and warm. But science has a habit of redefining the boundaries of what's possible. What was once impossible often becomes merely unproven. For now, we're left with remarkable hints. Entanglement is no longer confined to theory or deep space. It might live in the green of leaves, in the spark of thought, in the hidden unity of life itself. If that's true, then we must ask, where does entanglement end, and where do we begin? Quantum entanglement is far more than a strange quirk of physics. It's not a minor detail buried in textbooks or a passing curiosity of modern science. It is a thread, fine yet unbreakable, that runs through the very fabric of existence. It links not only particles but also entire disciplines, perspectives, and perhaps even consciousness itself. And as we reach the edge of that thread, we find ourselves facing a question that physics alone cannot answer. What does it mean? It's one thing to prove that entanglement is real, to confirm it through experiment after experiment, to use it in developing the foundations of a quantum internet, and to teleport quantum information across optical fibers with the dream of doing the same across space. But it's something else entirely to ask what kind of universe allows this to happen. We often call the quantum world weird, as if it were somehow less real than the everyday world we experience. But maybe it's the other way around. Maybe the quantum world is the real world, and what we experience daily is merely a simplified, averaged-out version of that reality, designed for survival, but blind to the deeper code beneath. Entanglement may be our first real glimpse behind that veil, and the timing of this realization feels almost poetic. In a world that seems increasingly divided, politically, socially, and environmentally, entanglement reminds us that connection is not only possible, but fundamental. Independence, while empowering, is never absolute. Even in a universe moving toward disorder, there exist systems that choose coherence, that bind rather than break apart. That alone is a quiet but powerful truth. Because entanglement isn't easy, it's delicate. It demands near-perfect balance to form and immense stability to sustain, yet somehow it endures. From photons forged in the cores of distant stars to ions suspended in human-made vacuums, entanglement refuses separation. It transcends distance. It defies isolation. It insists on unity. For some, this notion is unsettling. It challenges our cherished ideas of individuality and control, of neat boundaries between observer and observed. But for others, it brings peace. It hints that the cosmos may not be a machine at all, but a living web, a quiet harmony of interconnected patterns, each note resonating with every other. And what are we in that web? Are we just a fleeting arrangement of atoms, a brief flare of order in a sea of entropy? Or are we something defined by connection, something that becomes real only through relationships? Entanglement in this sense becomes both metaphor and mechanism. It invites us to see the universe differently, not as a collection of isolated events, but as overlapping ripples of shared resonance. It tells us that to observe is to participate, and to know is to become part of what is known. That idea doesn't make us smaller. It deepens us. It doesn't mean we are less real. It means reality itself is richer than we ever imagined. And so, as this exploration nears its end, we circle back to the question that started it all. Are particles even real? After everything we've seen, the double-slit paradoxes, collapsing wave functions, the ghostly ties of entanglement, the answer might not be a simple yes or no. Maybe the better question is whether reality is built from particles at all, or from relationships, from dynamic connections that reveal themselves only when they interact. Whatever the case, one truth emerges. Entanglement is not a trick of measurement nor a computational glitch. It is the matrix itself, the hidden symmetry beneath everything that exists. When you stare too deeply into quantum mechanics, the edges of language start to bend. You begin to sense that we might have been asking the wrong questions all along, that real may not mean what we thought it did, and that perhaps the universe cares less about things like particles, waves, or time, and more about the invisible relationships that bind them all together. Entanglement is no longer theory. It's fact. It's been tested, verified, challenged, and rebuilt. We've sent entangled photons into orbit. We've used them to encrypt data, teleport quantum states, and synchronize atomic clocks with unmatched precision. Yet, for all our achievements, we still don't understand why the universe allows this. Why should two particles light-years apart share a fate? Why should observation here affect results there? Why should a seemingly cold and silent universe be governed by something so profoundly connective? Maybe because entanglement isn't a rule, it's a signature, a subtle mark that says the universe isn't built from objects but from interactions. Not matter but meaning, not things, but relationships. Think about what we've uncovered, from the spin of paired electrons to the teleportation of quantum states, from violations of Bell's inequalities to the hypothesis that space-time itself may emerge from entanglement, from the molecular choreography inside chloroplasts to the electrical hum of the human brain. Entanglement keeps appearing, not as an anomaly, but as architecture. It doesn't hide behind physics, it builds physics. The deeper we look, the more it becomes clear. Entanglement isn't just part of reality, it is reality. Behind every equation and every measurement lies a simple truth. Nothing exists alone. Even the empty space between stars may hum with unseen correlations. And maybe, just maybe, so do we. We are quantum beings, made of the same fields and forces that bind the cosmos. If entanglement is the language of the universe, then each of us is written in that script. Not just our atoms, but our thoughts, choices, and awareness. Every act of observation changes what is observed. Every act of understanding leaves a mark, and every mark is part of a vast web that stretches beyond comprehension. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.